Good day everyone, and to you ma'am, good day. In this video, we, the group 7, are going to report all about molecular geometry. In this topic, the reporters is me, Jasami Magno, Vanessa Pangulibay, and Jasal Pitiluna. In this topic, of course, we will discuss the molecular geometry of every molecule, and also we discuss the polarity of molecules, hybrid orbitals, and covalent bonding, as well as the orbital overlap. Okay, what is molecular geometry? When we say molecular geometry, it is also known as the molecular structure that studies the three-dimensional shapes molecules form and how these shapes relate to the chemical reactivity and physical characteristics. A molecule shape can affect the physical properties of the molecule, such as freezing point, density, and other properties. For example, the shape of the water molecules makes water's solid crystalline phase, or it was called ice, less dense than its liquid phase at certain temperatures. This is an unusual property for chemical compounds, as most compounds have a denser solid phase than liquid phase. This is all related to its molecular shape. A central atom. That a central atom is an atom bonded to multiple other attached atoms. There are basically two main groups of geometries possible based on that number of attached atoms to a central atom and whether a central atom has non-bonding electron pairs present. The first group is when there are two or more attached atoms and no non-bonding electron pairs on the central atom. And in this case, the number of atoms determines the shape of the molecule with 5 main shapes. So what are those 5 molecular shapes? Those molecular shapes are named the following: the linear, triagonal planar, tetrahedral, triagonal, bipyramidal, and octahedral. Okay, first, for you to be able to know the linear is when if a molecule only has 2 bonded electron pairs and no lone pairs, it forms a linear molecule. As you can see in the picture, the electron pairs will repel each other equally and the result in an angle between the two bands of 180 degrees, and that's what we call the linear shape. For you to be able to know what is an example of the linear and you will identify the linear, one example of that is beryllium chloride. As you can see in the picture, although beryllium is a metal, it can bond covalently to chlorine. That the beryllium only has 2 electrons in its valence shell and so forms 2 bands. The electron pairs will repel each other equally and resulting in an angle between the 2 bands of 180 degrees. Next is molecules with 3 banded electron pairs, known as triagonal planar. In the picture, you can see this is because the band angle between each bond is 120 degrees, so the bands lie flat on a plane. Example of this is boron trifluoride. That boron trifluoride does not contain any lone pairs. Hence, the covalent bonds get separated by 120 degrees to have minimum repulsions between them. Therefore, the molecular shape of boron trifluoride is triagonal planar. The third molecular shape is tetrahedral, that is molecules with 4 bonded electron pairs and also no lone pairs form a tetrahedral shape. This is a regular triangular based pyramid that all the band angles are 109.5 degrees. That one example of this is carbon and methane, which is in the picture where the band angles are 109.5 degrees. We go to the shape of triagonal bipyramidal, that these molecules with 5 bonded electron pairs form a triagonal bipyramid, and this shape is similar to a triagonal planar molecule but with two further bands held at 90 degrees extending above and below the plane. One example of this is phosphorus pentafluoride because it has 5 regions of electron density around the central phosphorus atom and 5 bands but no lone pairs. The resulting shape is a triagonal bipyramidal in which 3 fluorine atoms occupy equatorial and 2 occupy axial positions. The last shape is octahedral, in that a molecule has 6 bonding pairs compared to other shape that around the central atom, and all of the bonds are at right angles to each other. And the example of this is sulfur hexafluoride, which has 6 regions of electron density around the central sulfur atom. So those are the molecular shapes, and now we proceed to the VSEPR model or VSEPR model, which stands for valence, shell, electron, pair, and repulsion. And now what is VSEPR? It is a model used to predict the geometry of molecules based on the minimizing the electrostatic repulsion of a molecule's valence electrons around a central atom. That means that we can use the VSEPR model to predict the geometry around the atoms, as of what I have said, that in a polyatomic molecule or ion by focusing on the number of electron pairs or groups around a central atom of interest. And groups include bonded and unbonded electrons, that a single band, a double band, a triple band, a lone pair of electrons, or even a single unpaired electron, each count as one group. Did you know that Ronald Gillespie discovered the VSEPR model? Yes, but the model was proposed by Neville Sidgwick and Herbert Powell in 1940, since Ronald Gillespie and Ronald Nylund then developed the model into their theory, or according to their theory that published in 1957. They are considered the developers of the VSEPR theory, as I have said earlier, that the valence shell electron pair repulsion or VSEPR theory can be used also to predict the shapes of molecules based on the number of the electron pairs around the central atom. In the basic shape, as you can see in the picture, as the electron pairs are negatively charged and will repel each other, the electron pairs around the central atom will adopt a shape that will minimize repulsion between them. Therefore, we need to be familiar with drawing dot and cross diagrams to simple molecules pairs first before we can apply the VSEPR theory correctly. So based on the total number of electron pairs, there are a few distinct shapes and band angles that we need to memorize, or we need to familiarize to easily understand them. The 2 electron pairs are linear, and the 3 electron pairs are triagonal planar, and the 4 electron pairs are tetrahedral, and the 5 electron pairs are triagonal bipyramidal, and the 6 electron pairs are octahedral. And I already discussed it. The actual shape depends on the number of bond pairs and the lone pairs around the central atom. In VSEPR theory, that a single band, a double band, a triple band are all treated as the band pair each. When we name the shape of the actual molecule, we do not take the lone pair into consideration, but the lone pair still exerts our repulsion and affects the shape of the molecule. Also, the repulsion involving a lone pair is greater than the repulsion involving a band pair. Hence, the presence of a lone pair will decrease the band angles as well as squeeze the band pairs closer together. An estimate that is useful to determine the band angle without memorizing is that for every lone pair, that the band angle will decrease by 2 degrees. Okay, I will be discussing again in the 2 electron pairs, it is a linear if it has 2 band pairs and 1 lone pair. And the 3 electron pairs, if it has 3 band pairs and 1 lone pair. It is trigonometrically planar if it is 2 band pairs and 1 solitary pair are bent. In the 4 electron pairs, a tetrahedral has 4 band pairs plus 1 lone pair. If it is a 3 band pairs plus 1 lone pair, it is a trigonometric pyramidal, and if it is 2 band pairs plus 2 lone pairs, it is a bent. And going in the 5 electron pairs, it is a trigonal bipyramidal if it has 5 band pairs plus 1 lone pair. And if you have 4 band pairs plus 1 lone pair, it is a seesaw. And in a 3 band pairs plus 2 lone pairs, it is a T-shape. If it has 2 band pairs plus 3 lone pairs, it is a linear. And going into the 6 electron pairs, if it has a 6 band pairs plus 1 lone pair, it is a octahedral. And if it has 5 band pairs plus 1 lone pair, it is a square pyramidal. And if it has 4 band pairs plus 2 lone pairs, it is square planar. And if it has 3 band pairs plus 3 lone pairs, it is a T-shaped. And the last, if it has 2 band pairs plus 4 lone pairs, it is a linear.
This is Jassel Pitiluna, and I am going to report on polarity of molecules. What is the significance of polarity of molecules? The polarity of a molecule could tell us whether the electron cloud is equally distributed across the atoms within the molecule, or whether an electronegative atom is affecting the electron density. The distribution of the electrons will affect the behavior and reactivity of the molecule. For example, you can predict which solvents will be most effective with a given chemical if you know its polarity. Like in the case of water and oil. Water and oil do not mix well despite the fact that they are both homogeneous solutions on their own. This behavior can be explained through a deeper look at the polar forces affecting the two solutions. There are 2 types of molecules according to its polarity. First is the polar molecules. It occurs when 2 atoms do not share electrons equally in a covalent band. A dipole forms with part of the molecule carrying a partial positive charge and the other part carrying a partial negative charge. This happens when there is a difference between the electron negativity values of each atom. Some examples of polar molecule include water, ammonia, sulfur dioxide, hydrogen sulfide, and also ethanol. Why we can say that water is a polar molecule? Water is a molecule composed of 2 hydrogen atoms and 1 oxygen atom. Oxygen is denser compared to hydrogen, causing its electronegativity to increase or its ability to attract electrons, giving it a partial negative charge. On the other hand, hydrogen has a lower electronegativity, giving it a partial positive charge. This unequal sharing of electrons between atoms creates a dipole moments or 2 poles, which is the positive and the negative. Therefore, water is a polar molecule because oxygen and hydrogen have different electronegativity values. We have another example. Sugar, which is a common name for sucrose, has a molecular formula of C12H22O11 and has this structural formula. The bond between oxygen and hydrogen creates a dipole moment, giving a partial negative on the oxygen atom and a partial positive on the hydrogen atom, just like water. This makes sugar a polar molecule. The second type of a molecule is nonpolar molecules. It occurs when electrons are shared equally between atoms of a diatomic molecule or when polar bonds in a larger molecule cancel each other out. In chemistry, nonpolar molecule has no separation of charge, so no positive and negative poles are formed. Some examples of nonpolar molecules include carbon dioxide, benzene, methane, and also ethylene. Let's see an example. Why oil is a nonpolar molecule? In oil molecule, the long fatty acid chains mainly contain carbon-hydrogen bonds, have essentially no dipole moment. Therefore, oil is a nonpolar molecule. Generally, the more carbon and hydrogen atoms a molecule have, the more nonpolar it will be. Another example is kerosene, having a molecular formula of C610, H22, and is a long chain of hydrogen and carbon atoms. We call it hydrocarbons. Its molecule has definitely no positive and negative ends, thus making kerosene a nonpolar molecule. There are factors predicting polar and nonpolar molecules in order to determine whether a molecule is a polar or a nonpolar. First is pyramid-shaped and V-shaped molecules are said to be polar, whereas the linear molecules are said to be nonpolar in nature. For example, water is a polar molecule since it is like a pyramid in shape. On the other side, carbon dioxide is a nonpolar molecule since it is in a linear shape. Second, fats, petrol, oil, and gasoline are said to be nonpolar molecules as they do not dissolve in water, and nonpolar is insoluble in water. Lastly, we can determine if a molecule is polar or nonpolar through its electron negativity differences or values. Therefore, if you already know the polarity of molecules, you can able to predict whether or not they will mix together to form chemical solutions. The general rule is that like dissolves like, which means polar molecule will only dissolve into other polar liquids, and nonpolar molecules will only dissolve in nonpolar liquids. This is why oil and water don't mix, because oil is a nonpolar molecule while water is a polar molecule, thus they will not form a solution.
So now we are going to proceed in discussing what is covalent bonding and orbital overlap. First of all, we are going to define what is covalent bonding. So covalent bonding are sharing of electrons to complete the outer shell or valence electron of the atom. So when two or more atoms are sharing electrons in order to complete the outer shell or the valence shell of the both atom, that is what we call covalent bonding. As what of the recent reporter explained that a covalent bonding aims to complete the shell or the octet role of an atom structure. So those atoms are commonly known as a non-metal atoms, or what we call the covalent compound. So from the word co, which means share, and valent means valence electron. So we have to take note that each atom must give or contribute at least one electron to the other atom. So next, we are going to define what are the types of covalent bonding. So first of all, there is single covalent bond in which we observe a sharing of 2 electrons. And then the double covalent bond is sharing 4 electrons, while the triple covalent bond sharing 6 electrons. So let's proceed on citing a example of covalent bonding, which is the chlorine. So in this example, let's take a look for the example of chlorine that each atom of a chlorine has only 7 valence electrons, which means each atom is still in unstable state, which means that it does not comply the octet rule or having a complete 8 electrons at each atom. So this chlorine atom will form single bond by sharing their valence electron concentrated in between the both atoms locked in between by magnetic attraction. As you can see to the second figure, there is a sharing of electrons of the both atom of the chlorine. So the outermost shell or the valence shell of an atom must contain 8 electrons. This is according to the octet rule of all atoms except po sa helium and hydrogen, because helium and hydrogen are both has a outer shells with only 2 electrons capacity. So next we are going to proceed to tackle the orbital overlap, or a refer to a two or more orbital from adjacent atoms in the same regions of space emerges, which lead the formation of bond. So this is where when two or more orbitals form adjacent atoms in the same regions of space that emerges. This orbital overlap lead to a formation of bond. So let's take a look of electrons character in this bonding. Electrons are moving around orbitals. The better the orbital overlap, the better the sharing, the stronger the bond. So if that covalent bond compound or the two nonmetal atom emerges, they create an orbital overlap. And so, like for example, in chlorine. Chlorine, as our example, the adjacent orbit of our two chlorine overlap together with the bonding of the single covalent bond, or the two shared electrons between the two atoms of the chlorine. So, when the bonding of the single covalent bond of two shared electrons, they finally experience the orbital overlap. We should take note that during the covalent bonding, the valence electron, the participation of atom sizes, and valence electrons matter. And also, we should remember always that the greater the overlap, the stronger the covalent bond will form between the two atoms of an element. On the other hand, overlapping also depend on their perspective phases and sign of interacting orbitals, such as positive overlapping of atomic orbital, or when two interacting atomic orbital is the same, then the overlap is positive and this lead to the bond formation. So in positive overlap of atomic orbital, when phase of interacting atomic orbital is the same, then the overlap is positive and this will lead to bond formation. Remember also that two interacting orbitals depend on the sign of orbital wave function and not on their charges. While on negative overlapping of atomic orbital, it is when two interacting orbitals are in opposite phase, then the overlap generated is negative and the bond is not formed. Meanwhile, in negative overlapping of atomic overlap is when two interacting orbitals are in opposite phase, then their overlap generated a negative charge and the bond will not be formed. While lastly, on zero overlapping of atomic orbital, when two interacting orbitals are not overlapping each other in an orbital. While in zero overlapping of atomic orbital, there is two interacting orbitals which is not overlapping to each other, and also there is no bond that is formed. So as you can see in the negative overlap, there is a no bond that is formed. While in a positive overlap, there is a bond that is formed. And the same with zero overlap and negative overlap, the both overlap has no bond that is performed. So that is all for covalent bonding and orbital overlap, and let's proceed to the next discussion.
What is hybrid orbitals? Hybrid orbital is an orbital formed by the combination of two or more atomic orbitals. The resulting orbital has a different shape and energy than the component orbitals that formed it. In other words, hybrid orbitals form when different orbitals in a single atom combine together to produce a hybrid orbital for bonding purposes. Hybridization is what we call the process of mixing two atomic orbitals in order to give rise to a new type of hybridized orbitals. There are three types of hybrid orbitals. Actually, there are different types of hybrid orbital, but these are the three basic hybridizations. First is the sp hybridization. This happened when one s and one p orbital goes in the process of mixing energy to form a new orbital. Such kind of hybridization is called sp hybridization. The molecules possessing sp hybridization used to have a linear shape with an angle of 180 degrees. Like this, for example, beryllium dichloride. In order to know about the hybridization of beryllium dichloride, we have to take a closer look at the central atom, which is beryllium. Its electronic configuration is 1s2 and 2s2, where 2 electrons are present in the valence shell. During the formation of beryllium dichloride, the beryllium atom bonds with 2 chlorine atoms via single covalent bands. The number of electron pairs around the central atom will be 2. No lone pair is found in the molecule. Since its total number of electrons is 2, then we can conclude that beryllium dichloride has an sp hybridization. The second type of hybridization is the sp2 hybridization. It is observed when 1s orbital and 2p orbitals undergo mixing of energy for equivalent orbitals to form a new hybrid orbital called sp2. An example of sp2 hybridization are ethylene and benzene. The third one is the sp3 hybridization, when 1s orbital and 3p orbital from the same shell of atom mix together to form a new equivalent orbital. Then this is called the sp3 hybridization. The best example of sp3 hybridization are ethane and methane. The nature of the types of hybridization. Hybridization is also a concept helps explain the molecular structure and shapes of the molecules. This table summarizes the type of hybridization, the shape, the band angle, and the number of orbitals participating in hybridization. sp hybridization is linear in shape. It has a band angle of 180 degrees and the total number of orbitals participating in hybridization is 2, since it consists of 1s orbital and 1p orbital. sp2 hybridization is planar and trigonal in shape, having a band angle of 120 degrees and the total number of orbitals participating in hybridization is 3, since it has 1s orbital and 2p orbitals. In sp3 hybridization, it is a tetrahedral in shape. It has a band angle of 109.5 degrees and the total number of orbitals participating in hybridization is 4, since it consists of 1s orbital and 3p orbitals.